Hello, my name is Tom Walski with Bentley Systems. I'm here today as a member of the Water Distribution System Analysis Task Committee of the Environmental Water Resources Institute. Today we're going to be talking with Jeff Cruickshank of Hazen and Sawyer about his experiences in water distribution system analysis. Today is October 13th, 2015, and we're recording this at the AWWA Water Infrastructure Conference in Bethesda, Maryland. Jeff, you've been working in the water distribution system analysis field for a long time. What got you interested in this field? What is your background and how did you get involved with this?
Well, when I was an undergraduate at Michigan Tech, I had a class in water distribution analysis that I enjoyed, and I was about halfway through getting my master's degree and decided to interview with a few companies sort of for practice so that the following year when I had my master's thesis done I'd know better what to expect. So I interviewed with this company called Photometers Associates, who used to come up to Michigan Tech every year, and they offered me a job pretty much doing what I had been doing in this class that I enjoyed. So that's kind of what got me started in water systems.
Okay, well, Photometer is known more as a testing company than a hydraulic calculation company. Things have sort of changed over the years in that you don't see nearly as much testing work and a lot more hydraulic analysis. How did you guys do that transition?
Well, that's a good question. You're right, Photometer was mostly known for leak detection, but they also did hydraulic investigations and modeling, and so they usually started people with leak detection, and that kind of went in one ear and out the other. I sort of filtered that out and focused on the part about modeling. That was the part that interested me. But my first job was a leak survey, and that was night work, so you had to go into work at like 10:30 at night, and you got out at 5 in the morning. And I did that for one job, and I told them, I'm done, I can't do this. I couldn't deal with working at night, and so they told me that, well, rather than losing me, they would try me out for modeling. So that's kind of how I made the transition from testing into modeling, and that is the reason why I stayed with them for what turned out to be 27 years.
Okay, yeah, the company, I remember talking to some of their guys in the old days, and they would say, oh, we don't need any models because we can just go out there and measure the flow, put a pitot rod in. But there's limitations what you can do with a pitot rod, right?
Yeah, well, you know, a lot of what they were doing, they hadn't kept up with. Well, they were kind of in the transition. So in the old days before models, they did Hardy cross analysis, like a manual iterative calculation with just banging out a lot of numbers on slide rules or eventually calculators. But the closer you were to, when you had to assume the flows in like a network, so the closer you assume those flows to the actual values, the fewer iterations you'd have to go through to arrive at the right answer. So they would skeletonize the water system down to a certain number of loops. Then they'd go out and make all these flow measurements so they knew what the flows were in each pipe, and that let them do the analysis more efficiently. So that kind of evolved, so they started doing more tests to calibrate models, and there were some people in the company who didn't believe much in models, and there were other parts of the company, like in North Carolina, where there was a lot of growth and modeling was a bigger part of their business. So that's eventually where I moved to, because that was the kind of work I was interested in doing.
Okay. And what kind of software did you use back then?
Well, when the first software, different offices used different software. So the Chicago office where I started used some software called Dallas Computing Services. Dan Brock was a guy who worked for the Dallas Water Utilities, and he ran this little business at night where we would send him punched cards, and he would load them into this giant computer at night, and then he would it would print out results on like computer ledger paper, and then he would mail that back to you. So the turnaround for one steady state problem was about a week, and they charged $1 a pipe. So if you had a 500 pipe model, that was $500. So you would, you know, make your run, wait for a week to see what happened, and then you would go from there. So needless to say, you didn't do like as many simulations as we do now. It was just like everything was stripped down to the bone. So that was how the Chicago office did it. Then they had other offices. When I went to North Carolina, they had this like teletype machine that they would hook up to a telephone. I think it was like 300 baud. It went into the little muffs from the phone, and it used this a canned program from some online service, and the results were terrible. Like in the class that I had taken at Michigan Tech, they made us write a program to do Hardy cross analysis, and the program that I had written at Michigan Tech was better than the one Photometer was using. So eventually they went to, right not long after that, Don Wood came out with KY pipes, and so our Chicago office bought a copy of that, and they didn't like it because they didn't like the output that came out of the paper printed output. So I told them that I could make what came out of his program, since he gave you the source code in Fortran. I told him I could make that look exactly like Dan Brock's program in Dallas. And so all I was doing was changing format statements in Fortran. They thought it was a miracle, so that for a while that was the program we used for probably 10 years. It was like the Photometer version of KY pipes, and I think most of the other consultants had their own version of KY pipes. But so that was that was the software that I first got involved with.
Okay, then you went to another one, WaterMax, was it?
Yeah, after a
eventually?
while, the KY pipes version of, or that Photometer used, was pretty much a steady state program. KY pipes could do extended period simulations, but we didn't really use it much. But KY pipes also had some graphics. That part of the program was written in BASIC, and it was kind of crude. Well, Max Old from Australia, he worked for Sydney Water for many, many years. I think he left Sydney Water and went into business for himself. He started coming over to AWWA conferences, and we saw his program. This was still in DOS, but he was so far ahead of everybody else on the graphics, true to scale maps, and just the way his program, you know, the text tables, the old way of looking at it, was integrated with the mapping on the screen and the EPS traces that you could do. So we recognized that was a better program, so we switched to that for a number of years. And then then when the transition to Windows came, he was a little behind the curve on that, and also he was behind the curve on reading shape files, moving shape files in and out. So we eventually just went with the commercial programs, and pretty much now is whatever our clients prefer is the software that we use.
Okay, so Photometer Associates was a well-known company. Just about every city in the United States had a photometer report on the shelf, or several of them on the shelves. So the history of that really came out of John Cole, who invented the pitot rod to measure flow in pipes under pressure, and it was handed down generation to generation. So whatever happened to Photometer Associates?
Well, when I started with them, Shaw Cole, who was, I think, the third generation of the Cole family, he was the chairman of the company. And Bill Hudson was the president in Chicago. Shaw Cole was in New York. So he ran the company until he became ill. And then his son, Bruce Cole, who had been in the insurance industry, came in and ran the company for a while. They eventually, he ran the company with Mo Seidler and Bill Gross. Well, they were all about the same age, and when they were ready to retire, they decided to sell the company. So they sold Photometer Associates to Severn Trent, which was one of the English water utilities that got privatized when Margaret Thatcher was in office. So they bought the company for a while, and they were running it when I left. And then I think they sold what was left of Photometer to ADS, if I'm not mistaken. And so now there's not sure if there's anything left of the original company. It kind of disintegrated.
So most of the guys that you worked with have retired or passed away, and there's only a couple left out there.
Yeah, there's still some. What happened to most Photometer folks is sooner or later they got tired of traveling around, so they would usually go to work for water utilities. So there were a lot of water utilities with Photometer people running them or in their organization. There are still a few, but they're fewer every year. But it used to be everywhere I went, I'd run into ex-Photometer folks because they were in business for a long time. I think they started in like 1896, and I think Severn Trent probably bought the company in the early or late 1990s. So they were around for a long time, and a lot of people moved through Photometer Associates. They generally hired people right out of school because you had to travel around like a gypsy to different water utilities. So you got a whole lot of experience in a short time, but the price you paid was you were always moving around. So people would usually get married and have kids and leave the company and go to work for water utilities.
Okay. So another famous company you work with is Hazen and Sawyer now, and Hazen is another famous name in the water industry. Where did that, how was that connected to the Hazen-Williams equation?
Yeah, Alan Hazen was one of the most prominent hydraulic engineers ever, I think. He helped build the Panama Canal, and he helped design some of the earliest water plants. And he was if you Google Alan Hazen, you'll find a very large volume of information about him. So his son Richard Hazen started Hazen and Sawyer, and they started the company in about 1950, I believe, and in New York, and they branched out into other cities. I have an old Hazen and Sawyer report. I think it was written in 1952, and if I remember right, they had an office in New York and an office in Detroit. But that's how Hazen and Sawyer started, and a lot of the people I work with now at Hazen and Sawyer remember Richard Hazen. He's passed away now, but he was still involved with the company until not that long ago.
So you've worked on a lot of studies over your life, I bet. Like, how many studies do you think you worked on in your career?
Well, some of the studies that I did were like, you'd fly in and fly out, and it was a 2-week testing thing. But the water, like master plans and modeling studies, usually at least 2 or 3 a year, and I've been doing it for 40 years, so over 100, I would say.
Yeah. So are any really memorable ones? Any that you want to tell some interesting war stories about?
Well, that's what always interests me. That they're all interesting, and they're all different, and they all have their own little quirks, and that's one of the things that always interested me was how each system you had to learn about it, and it had different topography and different history the way it had developed. So. But the ones I remember, or one I remember in particular, was Oklahoma City. That was one of the largest systems that I did early on. I think the first time I worked there was in 1978. And I can remember looking at a map of Oklahoma City, and it was perfectly laid out in grids, like 1 mile square patterns on a map. And I remember showing that map to people in North Carolina, and they thought I just made it up, like to show it was a model composed of squares. And they thought, well, that looks like something you just sat there and drew with a ruler, but that's the way the city was laid out. And that was interesting for several reasons. One was, we used to do C-factor tests where we would go out and measure the flow and measure the head loss and calculate the C-factors. So they had a water plant that had 48-inch pipes coming out of it, and it was relatively, it was their newer plant, might have been 20 years old at the time. And I measured C-factors of 80 on 48-inch mains that were only 20 years old. And that seemed, or less than 20 years old, and that seemed very unusual, and at first I didn't believe it. So I repeated the test 2 or 3 times, and in the end there was no doubt that was what the C-factor was. And you could break it into pieces. That's how I ruled out closed valves. I could do it in all different pieces and get the same thing. Closer I got to the water plant, the lower the C-factors got. Well, about a month later, they took a piece of that pipe out of service to build a Santa Fe railroad yard, and there was pieces of it lying on the side of the road. And on the inside of the pipe was this stuff that looked like cardboard, and I could take a knife and scrape it off the inside of the cement mortar lining. So it would come off in sheets, and it was rough. It wasn't smooth. And I had a textbook that had a table for culverts, corrugated culverts, where you had the spacing of the ridges and the depth of the ridges. So I used that formula to approximate what the C-factor would be for this stuff that I scraped off of this pipe, and it worked out. I think what I got theoretically was something like 90. And when you considered all the butterfly valves and every other thing, this 48-inch main had 36-inch butterfly valves. So if you factored all that in, that made me a believer in one of the many things that made me a believer in the equations for hydraulics work, and that explained why this pipe had this low C-factor. It was coated with lime and alum, and it wasn't a smooth coating; it had roughness. And that was the reason for the low C-factor. And I was amazed at how little of that coating it took to cut the capacity of that pipe by like 35%.
Yeah, that's probably Morrison Wiggert's book, probably Applied Hydraulics.
I think you're right.
Yeah.
I think you're exactly right.
It was part of the library when I was with the Corps, and so I never took it with me. I should have stolen it, because that was a really good book.
It was. You're exactly right. That was the textbook that I had used at Michigan Tech.
Uh-huh.
Bob Baylod was the hydraulics professor that I had, and he was probably the best teacher I had in college. That guy, I learned enough from him in 1 year to last me the next 40 years. He gave me a pretty strong background in hydraulics.
Okay, so nowadays you're still doing a lot of modeling work?
We are. That's pretty much all I do now, and has been all I've done for quite some time. I supervise other people who do modeling, but that way I get even more different systems to look at. So I have a lot of perspective from looking at a lot of different water systems. And one of the things that's been interesting to me is that during my career, two big things have happened. One is we've changed from mainframes where you mail stuff and it takes a week to get the answers back, to PCs and all where the screen blinks and it just went through this EPS simulation. That never ceases to amaze me. So that made it possible to try so many different alternatives and model different, instead of just 1 or 2 simulations, you can look at all different kinds of trials. So that was a major change that I thoroughly enjoyed. And the other thing that happened was water quality modeling kind of came into play during my career. I think in about 1993, EPA-NET came out, and that opened up like a whole new part of modeling for me. And that was an interesting part of modeling that I hadn't been exposed to previously. And now there are even more applications, just because modeling has always been right on the edge of what computers can do. We used to be like limited by computers, and now that computers are so much powerful, we can do a lot more things with a model.
Yeah, but researchers have been doing a lot of work at optimization, yet it really hasn't caught on. Do you ever use any optimization stuff?
Not a lot. We've talked about it, but our experience has been in a water system, there are so many unknowns and such big tolerances on what you know. Like you might know a C factor, but it's plus or minus, 5 or 10%. All the flow estimates, have an error tolerance, and we've never really had an application where it seemed like genetic algorithms or something would be applicable. One of my concerns is that they'd be if you know everything and there's nothing strange out there, you could use it, for example, to fine-tune the C factors in a model. But it also seems like a really good way to hard boil a closed valve into your model. So instead of like going out and finding the problem and fixing it, you've just polluted your model with this by forcing it to fit the measurements and thinking that it's the C factor. And so, you can constrain the C factors that the optimization uses, but I just don't think modeling, from my experience, is that exact of a thing that you can get it right down to, like, anybody who ever puts a decimal point on a C factor is just like fooling us all. And also even even pipe sizing is kind of the same. Like if usually it's not that, like, pipe sizes come in increments. You usually don't install a 23-inch pipe. So it seems like it's usually pretty obvious if it should be a 16 or a 24. And I don't see where the optimization can help make that decision in most cases that I've used a model for. I have seen examples from the vendors, like the New York water tunnel problems and all of that. There are some cases where optimization would be good, and it might be good for wall decay coefficients for water quality modeling. So I'm not saying there aren't applications where you could use it, but I don't see it as like a real one of the main tools in the toolbox.
Okay. So standing back now, looking at your career over 40 years, what do you have to say about what you've seen happening and what the future looks like for this kind of analysis?
Well, I think that just tying things together, like tying the model to SCADA and being able to access the data, that seems like a big step forward, or it's going to open up. We'll be able to do things like look at non-revenue water in pressure zones or in geographic DMAs, or whatever you want to call it, in a water system. So I think just being able to like integrate information from lots of different sources, that's going to be something that I'm sure there will be more of in the future. But one of the main things that I've seen, and I think if you talk to people who do a lot of modeling and calibrating models, closed valves are a really big problem in most water systems. And I think anybody who's worked in the industry knows that, and it doesn't reflect poorly on the person running a water system because it's a cumulative thing. And but I think most water systems have before they spend a lot of money on improvements, the number one thing they should focus on is closed valves, because they're very common. And now that we build models that have all of the pipes, and they're not skeletonized, they have all the pipes in them, the models assume they're all open. And in most cases, there are a lot of them that are closed, and they affect the results, and they affect water quality, and they affect fire protection. And they're a major problem, and it's getting worse instead of better as people pare back their budgets. So I think that is something that needs to be addressed in the future.
Okay, great. Well, we really appreciate you taking the time to help us out with our history committee and give perspective from your experience, because we'd like to get a broad range of people, from the actual consultants that did the work to the developers to the researchers, and you gave a really good perspective from your experience. So thanks a lot, Jeff. We appreciate it.
Well, thank you.